same time, knowledge that you need to have kind of already known. So we're going to look at number lines and real numbers. Simple number lines, right? You should all know that already. We're going to compare values and their characteristics, and we're going to talk about absolute value. So let's start first. We have some subsets listed here, and I was already nice enough to put this little diagram. Can somebody explain this diagram that has a little bit more knowledge? Tristan, start us off.
So this is the type of numbers that exist in the world. Some are irrational, some are real, some are not real, some are rational.
So what's the whole idea, Tristan? Why are there sets within sets? What can you explain the nature of the arrangement I'm saying?
Because all natural numbers are whole numbers, and all whole numbers are integers, and all integers are rational numbers.
And all rational numbers are
real
numbers. So the major category is real. In this year, we're going to learn about imaginary numbers. If you've already learned about them or you've heard of it, that's fine. But we're going to do a little bit more than probably you've done in your algebra class in middle school. And we're going to learn about applications of imaginary numbers. So I studied engineering, I know you guys. Imaginary numbers are extremely important in electrical, computer, and systems engineering. So have you ever ridden on an airplane before? And, well, first of all, how many people have ridden on an airplane? Okay, or flown, not ridden, flown. Or even in a car that has cruise control. So an airplane, once they lift off, it's pretty much cruise control. You know that, right? Pilots, they don't do much once it's lifted off, to be honest. There are certain circumstances, but for the most part, they hit go after that. So the plane has what's called a feedback system in it. And it allows for perturbations to be manipulated. So imagine you're flying and a gust of wind, or like there's a really bad air current. Part of the wind might cause the plane to do this. The plane knows instantly, within like a millisecond, to adjust these flaps on the side to change the pitch to balance back out. In a car, if you hit cruise control at 70 miles an hour, the car knows stay at 70. How does it stay at 70? It has what's called a feedback system. And it takes a little reading, and if the car is at 68, what does it tell it to do? If it's at 68, what should it do?
Stay at 60.
Well, it want to be at 70. So speed up. But if it goes a little bit over, then what should it do? It keeps happening. But it's happening so fast that you don't sense it. So when a car is on cruise control, it's literally doing that all the time. If you've ever put a car on cruise control, and I've done it because I lived down in D.C. for a couple of years after I went to college, and I would drive home to visit family, like a 5-hour drive, and I would be on I-95, and it's a highway, and when you're on a highway like that, there's no cars, instead of holding the gas down on your foot the whole time, you could just get to 70 miles an hour, hit cruise, turn it on, remove your foot, and the car goes. And then actually, what's cool, there's plus and minus too. You could make it like a video game. You could press plus to increase the speed, minus to decrease, and you never have to use your foot. But you never use this on a day-to-day basis. It's only when you have long trips. So the car, though, is able to use a feedback system that is able to sense the change in miles, change in speed or velocity, really, in that sense. So imagine you're in this car, now it's going uphill. When a car goes uphill, what does it have to do to maintain that speed?
Push harder.
Push harder. It has to work harder. More engine power has to be used or given up in order for the car to maintain that speed uphill. What about downhill? Yeah, if anything, you know what? Cruise control, it's so cool, and you should never do this, but if your folks are driving and you're in the driver's seat, watch the pedals. The pedals move on their own. It's cool as hell. Like, if you're going downhill and the car is picking up speed, what do you want it to do? Slow down. The only way to slow down is to do what? Brake. But cruise control, usually you think it only works on the gas. You'll see the brake engage on its own. It's really cool. So it's a system in the car, especially any car after like 2005 should have this now, you know? Where the car is able to maintain the speed. All of that, the reason I'm telling you about all of that comes from imaginary numbers. Believe it or not. And we're going to talk about how that works. We'll give you a little preview. It's a little bit difficult to go into the specifics because it involves like college level calculus, 3rd, 4th level math that you learn in engineering. But all that imaginary number stuff, it's always taught in high school and every kid goes, why am I learning this? Who cares, right? It's an imaginary number. That's the reason, and it's a huge portion of engineering that utilizes imaginary numbers.
Is it imaginary because the number's always moving?
It's not. It has to do with the nature of the number. For those that know where imaginary numbers come from, it came from the square root. And we'll talk about how the square root plays a role in that. And it's easy to tell you because it's very simple. Like, what's the square root of 25?
5.
Right? We all know that. What's the square root of 16?
4.
What's the square root of negative 25?
was the imaginary?
That's the imaginary portion. Because remember, square root means find two numbers when multiplied by itself gives you the bigger number. Right? Because 25, well, how do you know the square root of 25 is 5?
5 times 5.
It's 25. Can you come up with two numbers that are identical that multiply to give you a negative number? Is that physically possible?
Multiply to get positive.
Exactly. Because two negatives make a positive, two positives make a positive. So if the number is the same, it's impossible to get a negative answer. So that's where the imaginary number was introduced. Negatives under square root. Okay, but we're going to see how that plays a role to engineering also. So yes, these are subcategories. The whole other set of numbers is imaginary. So we are going to work with the real numbers for the majority of the beginning of the year. In the real numbers, they can be rational or irrational. What is the difference? What is the difference?
Well, rational numbers be put to A or B form, so you can put like a fraction. Like 1/3 is a rational number because it's 0.3 infinite. But irrational numbers are things like pi, where you can't put it into a fraction. It goes on forever and ever and ever.
Yeah, that's the general definition. Anything rational can be written as a fraction. Anything that's irrational cannot be written as a fraction. Now, there are other ways to make it a little bit simpler because you might not know, for example, that 0.1 repeating, that's 1/9. If you didn't know that off the top of your head, do you know that it can be made into a fraction? So we'll talk about decimal things as well. So first, rational numbers, let's start with that. So examples would be like 1/3, -2/5. An irrational number, the example that was given that everybody always gives is pi. Pi is an irrational number. Now, there are so many other irrational numbers. And I'm going to give you a hint as to figuring out how or what they are. Real or rational numbers, the decimals, what's the decimal of 1/3? What's the decimal equivalent of 1/3?
0.3.
Yeah, 0.3 repeating. I'll pick up with this tomorrow. I ran out of time. So you guys got lucky a little bit. No homework tonight. You're welcome to look ahead. If you want to look ahead at the 1-1 homework, we don't have to do it. We'll definitely pick up with this tomorrow. We might even run into 1-2 and just finish 1-2 tomorrow also. Okay? So we were talking about types of numbers yesterday, and we were talking about the difference between rational and irrational. And Annette told us that rational numbers can be written as fractions, whereas irrational numbers cannot. Now, you might be tempted to say, but you know what, Mr. Howell? Pi can be written as a fraction. Look, here's pi as a fraction. But anything over 1 is not really a fraction, actually. It's itself. So that is assuming that the denominator is a non-unity value. Okay, it's not going to be 1, obviously. Now, let's go back to the concept. So that is an easy way to remember. Fractions can be possibly written. You cannot write a fraction from the number. There's an easier way to remember them. Besides fractions is an easier way. And I was getting to it as we ended the day yesterday. Kate, you told me that 0.3 repeating was 1/3 at the very end of the day. So 0.3 repeating is a rational number. So what could you tell me about rational numbers in general then?
Numbers that repeat.
That have a repeating decimal. Well, what about -2/5, Kate? What's that?
That's 0.4.
Good. Negative, yeah, it doesn't matter that part. Well, that doesn't repeat, Kate.
So it can be like something that's a fraction, something that ends, like you can see an end.
Terminating decimal.
But it's repeating.
Or repeating. Let's write those three things down. Under rational numbers can be represented as fractions, repeating decimals, or terminating decimals. Again, rational numbers, fractions, repeating decimals, or terminating decimals. But isn't a terminating decimal just a repeating decimal, really? What number repeats always after any terminating decimal? 0. So really, if you want to be a little bit, a little snarky, you could say, it's really just repeating decimals, actually, Mr. Howell. Because every decimal that terminates is a repeating decimal with infinite zeros after it. Right? 0, 0, 0, 0, 0, 0 afterward. After this 0.4, you see zeros forever. So terminating decimal, repeating decimal, or fraction. What about irrational numbers then? You guys know. What do you know about pi? You all learn about pi. It's like, oh, this is great pie. Pie is actually pretty fabulous, especially apple pie. It's my favorite. But pie itself is fabulous too. What is cool about pi?
The digits are infinite.
The digits are infinite. What do you mean by that? Because the digits are infinite here, 3 repeating forever.
They go on forever, but it's not the same number of repeated. Yeah,
Not the same.
Not the same numbers.
It could be 191919 forever. Those aren't the same numbers.
There's no pattern.
No pattern.
pattern.
Good way to say it, right? Because again, 0.19191919 can be written as a fraction, actually, because it's 19 repeating. If you could find any portion that repeats at any point in time for any number, it is rational. If you cannot find any repetition at all of any pattern, it is irrational. That's why pi is irrational. There is no point in time where there is a repetition of a strand of numbers. Infinite repetition, I should say. What other numbers don't exhibit repetition in their pattern of decimals? It's not obvious. Well, give it a shot though. Go. Panic. I had you to raise your hand before I said that. You realize that it didn't work, or? There's a huge set of numbers that are all irrational. There are more irrational numbers than rational. That's going to blow your mind. Mind blown. There are more irrational than rational, actually. And you learn about that if you go on to take like advanced math in college and like proving and theories and stuff. It's cool. What kinds of numbers are irrational that we haven't mentioned yet? What? What is it? Draw it on your thing.
Wait, isn't there one number that's like 2.7?
Yeah, she's talking about square roots. Square roots. So, were you going to give that as an example by any chance, Tristan?
I was just going to say any number with the same.
Oh yeah, absolutely, but I was saying give me examples of those. So the simplest example is square roots. What's the square root of 25? So that's rational, isn't it? How about the square root of 24? Type it in your calculator. Root 24, go ahead and type it in. What do you get when you do root 24? Who's the first one that's got it? Second, you got to hit second. And then x squared. Second, x squared, I think. Should be right above it, right?
Oh, there it is. How do you know that?
I've seen a calculator in my head so many times, I have every button memorized. It's terrible.
Okay, 4.89894946.
So at first you're like, oh my gosh, look at that, 8989, right? Repeating, but then what happens? What was it after?
It's 7948.
I'm going to put ... okay? So, what you will recognize, and it's not something I'm going to prove to you right now, but it's something that's easy to write down. Any square root of non-perfect squares are irrational. So, is radical 16 going to work? What's the square root of 16? That's rational. That doesn't work, because that's a perfect square, isn't it? 16? What are your perfect squares? 1, 4, 9, 16, 25, 36, 49, 50, 64, 81, 100, right? You know your perfect squares by now. If you take the square root of any of those, you get an integer answer. So those are never going to work. So it's the square root of non-perfect squares or non-perfect numbers or non-squared numbers, whatever you want to say. Okay? Any of the numbers that are not perfect squares under a radical are irrational. Irrational. Yes? Make sense? If it doesn't make sense, you should ask, maybe, right? If there's any questions, if you're not sure, if something I said is not clear, if I'm slurring my words too much, whatever it may be, please ask. So do we understand the difference now, right? Repeating, non-repeating. Easiest way to remember. Everything that repeats can be written as a fraction. And if you want to see the proof of that or work on that, I can show you that also. Anything that repeats can be written as a fraction. Now, let's go into those other three sets real quick. We're going to fly through these next three. I hope you know them. Integers. How are integers different than rational numbers? How are integers different? They cannot have, let's say decimals for now. They cannot, because like 8 over 4 is a fraction, really. So every single integer does not have a decimal portion or a fractional portion, we could say. So integers, what are they? What are integers? Examples?
There's no, well, for an example, like 24, any whole number.
And it could also be what? What's the other part we have to think about? Integers can be good. Integers could also be negative. All of those are examples of integers. So integers are all the numbers from negative infinity all the way to infinity that are, as Kate said, whole numbers. Okay? And we're going to see whole numbers in a moment, how they differ from integers. How do whole numbers differ from integers? How do whole numbers differ? They don't have negatives. Okay, whole numbers start at 0 and they go up. If you want to write that down, you just write no negatives. How about natural numbers? This is one that most students honestly don't know, and it really doesn't matter. You're never going to use this in life. You're never going to use the concept of a natural number. Natural numbers just don't include 0. So it's all positives. Okay, so as much as you have to memorize this and know this, and you should know these terms, honestly, you're never going to hear about whole numbers and natural numbers and have to specify which one they are in some sort of advanced math. It's not going to happen. It's a waste of your time. Know the terms, but you really don't need to know these two as much. You should know what an integer is, though. Everybody in this room should know what an integer is. An integer is all the whole numbers and their negatives. That's what an integer really is. An integer is whole numbers, but all their negatives also. Okay? Integers do not have fractional or decimal components to them. They have to have only whole portions. All right, good enough. Yeah.
Why do you specify that all of this are real numbers?
Because in 5 months, we're going to talk about a whole other set of numbers that are not real. They're called imaginary. So these numbers, even though irrational and rational are two different things, they are still both considered real. The major subset or the major category is real. That breaks into irrational and rational, and then rational breaks up into its 4 categories. So we can see on the next slide, take a look at all of your definitions. If you wrote stuff down, that's fine. You wrote down your notes, you should have. These are all formal definitions of things, of those types of numbers. Read through them quick on your own. I'm not going to sit here and read these because we just talked about them all. If there's anything that doesn't make sense, please ask. Take a minute just to read through them. If there's something that doesn't make sense or isn't clear, let me know. The name for natural numbers could also be called counting numbers, and that makes it easier when you count things. You start with 0? No. You say 1, 2, 3. You don't say 0, 1, 2, 3. Nobody counts 0, right? You count with 1 on. So counting numbers is another name. Questions? Anything? All right, let's go on. So number lines. We know what number lines are. You better know what number lines are if you're in this class, right? Negative infinity to infinity. Very simple. Now, on a number line, we do not need to write every single integer. You're going to see throughout the year that you're only going to plot specific values on the number line. So please, if your older teacher told you have to go 0, 1, 2, 3, 4, and write every integer, you don't have to. We're going to see throughout the year that we might only be concerned with 2 locations on the number line, and then we have to do what are called shadings on the number line. And we'll see where those come up. So this is a number line traditionally, and the easiest thing, or the thing that's good about a number line is a number line teaches you about subtraction. It teaches you really well about subtraction. So, how do I subtract 5 minus 4? What's the answer, everybody? How do I know that? What's this distance? 1. That's what subtraction is. Subtraction is the distance between the 2 particles and 2 objects, wherever they are. So, Bridge, if I asked you to do 3 minus negative 4, it would be 7. And he knows that because when you minus a negative, it really means add. But really, look, here's 3. Here's negative 4. Oh, here's negative 4. How far apart are they, Bridge?
7.
7 units. 3 and negative 4 are 7 units apart. That's why 3 minus negative 4 is indeed 7. So a number line teaches us about the distance between 2 particles. You see this obviously in history class. Timelines. Timelines are number lines. In engineering, you're going to hear about things called Gantt charts. Gantt charts are timelines for projects that you work on. It's the same thing as a number line. What happens when I put 2 number lines together? What do I get? Yeah, coordinate graph, a Cartesian coordinate graph, whatever, a graph. I don't care what the term is, but it's a graph. That's what a graph is. It's just 2 number lines put together. Okay, that's all it is. Let's go to the next slide, look at some applications. Take a look at this problem first. Give yourself a moment to try and figure out the answer, and then I'll go over it with you. by the way, this is the easy version of this problem. We're going to do a difficult version in a moment. So 2/3 of the way from A to B. What does that mean? Is it closer to A or closer to B? Closer to B. Good, Bridge. Let's look at this because a lot of students have trouble with this first portion. Ready? If I were to look at this distance and I want to go 2/3 of the way from A to B, I go about there, about 2/3. Okay? If I think about this overall distance, how far is this overall distance? 6 units, isn't it? So if I put a marking here, here, and here, isn't it broken into thirds? 1/3, 1/3, 1/3? And those thirds are really 2 units long. This is 2 units, 2 units, 2 units. Because what's a third of 6? It's 2 units. 1/3 of, in math, times 6 is equivalent to 2. So if it's 2/3 of the way from A to B, I go 1/3 of the way, 2/3 of the way. Well, what's that coordinate? 2. Okay? Your answer is simply 2. It is not simply 2 because I did 1/3 times 6 giving me 2. It's because I started at -2, I added 2, and then I added another 2 to get back to 2. Again, starting here, 1/3 of the way, 1/3 of the way, and I'm here. If I want to do it this way, make it a little easier. What's 2/3 of 6? What's 2/3 of 6? 4. So if I want to go 2/3 of the way to here, I go 4 units. 4 units on top of -2 brings me to 2. So there are many ways to solve a problem like this, but recognizing that the distance between the 2 portions or particles or whatever locations is cut into thirds really, and then you go 2/3 of the way. All right? Seems like a simple problem, and it is pretty simple. Let's take a look at one that's a little bit more complicated. A little bit more complicated. Before you begin the problem, tell me one difference that you notice in this problem and the last one. Very good. Well done. And that's the thing I want to make sure we all understand. When you see parentheses S after coordinates, it means there may be more than one answer. Is that clear? So if it said find the coordinates with just an S, there would be multiple answers. If it said find the coordinate, there's one answer. But when you see this with parentheses around the S, in math, you're going to see this in the SAT, on all these kinds of tests. Parentheses S means there may be multiple answers if we didn't know that for some reason. So there's going to be, I'm telling you now, 2 answers to this problem. One of the answers is easy to get. Most of you can probably get it by looking at this. One of the answers is very easy to get. But the other answer is not as easy to get. Can you come up with one of them at least? Let's see if you can come up with one of them. What do you got? Tristan. Yes, Tristan is correct for the first one. -3 is half as far from A as it is from B. How far is -3 from A? Everybody, how far? How far is -3 from B? Isn't 2 half of 4? So Tristan is absolutely right that -3 is half as far from A as it is from B. Now, the other answer is not obvious at all. I'll give you a hint. Oh, does anyone get the other answer yet? Okay. I'll give you another minute. I think so too. You're on the right track. So you guys, you're on the right track. Keep going. Any ideas so far?
Yeah.
Negative. -1. You gotta go way outside the range. Go outside of A and B. Look at numbers out here. That's where you're gonna get an answer correct. Just tell me. I mean, don't tell me. Just show me.
I think I'm thinking really outside the box.
What's your answer?
6, because 6.
You did the opposite. 6 is half as far from B as it is from A, I think.
Oh, yeah.
You need it half as far from A as it is from B. You see what I'm saying?
Yeah.
So where should you be looking? Not over here.
Like, over there.
Good. What do you got? Good. Figure out why. I'm going to show you mathematical reasoning for this. A lot of you are just picking numbers and trying, which is fine. That's fine. Yeah, go ahead. Tristan, what do you got?
Because it's double the length from B, because it's the same length.
Yeah, think about negative 11. Negative 11 right now would be all the way out here, right? This would be the value that you're looking at. How far is that from A?
16.
And well, how far was A from B, guys? So the distance from A to B is 6 units. So wherever this number is, it has to be how far? Not 6 units, but 12 units away. So this distance from the point we're looking at to B is 12 units. The distance from the point we're looking at to A is 6 units. 6 is half of 12. Now, this has been arbitrary guess and check, hasn't it? Some logic. A lot of you picked up that it should be outside the range and all that stuff. Let's talk about math now and how we can get this answer. So keep this slide open, and let's pick and think for a second that we don't know any of this. So I'm going to try. Can I erase the slide? I can't erase all of it, can I? Some of it I can't erase, unfortunately. So let's imagine for a second that I don't know the answer. And I tell you, pick some value x. Call it x. And it's somewhere between there. And I want to figure out these distances relatively speaking. How far is x from A? I don't know what x is. If I want to write an expression that shows me how far x is from A, how would I write it? What did we talk about earlier? You did the example earlier, Bridge. What operation should we use to represent distance?
Sorry, I forgot.
Somebody help me out. Sorry. Absolute value?
Yeah.
With the bars? We're going to use absolute value, but before that, I want to represent the distance between x and A. How do I represent distance?
X minus A.
X minus A inside the absolute value, and we'll talk about why that is. So look, x minus A is this distance right here, isn't it? That's how you figure out distance. You take the larger number minus the smaller number. Well, we know A is negative 5. So this is really x minus negative 5. Now, what's the distance between x and B? What's the distance between x and B? Hannah, as an expression, how do I write it? B minus x. Very good, Hannah. And Hannah recognized to make it larger minus smaller. So you don't need the absolute value if you do it this way. But you could use it, it would work. So B, though, happens to be 1, right? And this is minus x. So this expression represents, again, the distance from A to x over the distance from B to x. Again, the distance between A and x is this. The distance between B and x is this right here. Well, those expressions are written. What should that equal? What should the ratio of the distance of A to x and B to x be? Look at the problem. What does it tell you? This distance here, let me point so it's clearer. This distance right here, do you see that? Should be how much of this? Half. So set this equal to 1/2 and solve. Solve that. Cross multiply. Go ahead and cross multiply and solve. Cross multiply and solve. It's clearly x plus 5, right? Minus a negative. Continuing this problem, cross multiplying. Distributing. And solving. Did you get negative 3? And what was our first answer earlier? You didn't get negative 3?
No, I'm just confused.
Let me explain again, no problem. So, first of all, remember the first answer that almost everybody got? It was negative 3, right? That was the easy one. Negative 3. Let me scroll up so you can see what the heck I'm talking about. Negative 3 was the answer earlier, remember? Because this distance is 2, and this distance is 4, so it's half. This location is half as far from A as it is from B. 2 is half of 4. So what I did instead of guessing is I wrote a proportion or a ratio. I said the distance from A to X over the distance from B to X, well, that should be a half, because that's what the problem is asking us. Well, what's the distance between A and X? It's X minus A, because X is bigger. Look at the problem. Isn't X bigger than A on the graph? But on the other part, isn't B bigger than X? So when I do that one, I have to do B minus X. But since A happens to be negative 5, this is really X minus negative 5. Since B happens to be 1, this is 1 minus X. This over this must equal 1/2. As a result, I could set that equal and solve. Now, that gives you only one answer. Where's the other answer? Physically, where was it? What was the answer? Some of you got it. What was the answer? The other answer? Negative 11, wasn't it? So if you were doing it for this one, where should your X go? Should it be in between A and B, or where should it be? Should it be in front, or should it be behind? Where's the answer?
Less than both of them.
Yeah, it's less than both of them. So after this, what you could have done is put a random variable X over here. Well, now take a look. What's this distance right here between A and X? How would you represent it? A minus X. Isn't that different than this? What's the distance from B to X? It's still B minus X, right? That's how you find distance, larger minus smaller. So this distance is B minus X, that's fine. But this distance now is A minus X. So switch these two around and resolve the problem. Again, switch these two around and resolve this problem. So cross multiply those two boxes there. Okay, solving for X. I'm going to add this X over, making that negative X. I'll add the 10 over, making that 11. So X is negative 11. So this is a bit of a difficult problem compared to the first one that was really easy. It was like, 2/3 from A to B. That's fine. It took 6, 2/3, simple, 4. But this problem, not only is the first one kind of tricky, if you see it, it's okay, but if you didn't see it, you have to set up the proportion. Yet there's a second answer in addition. Why will there never be an answer to the right of B for this problem? Why will there not be an answer, Luke, to the right of B?
Because all the things closer to B than
Yeah, and what do we want?
we want it to be closer to A.
Yeah, the problem said half as far from A as it is from B. So that means that our answer needs to be closer to A. This is 2. It's closer to A. This is 4. It's further from B. This is half. So if you put a number out here, or you put that little X, that red X, out here and tried it, it's going to be closer to B. It's going to be much further from A. So it can't be half as far from A as B. So this answer region over here is impossible. We could not choose an answer out there to test. Okay? Tricky problem. Definitely not one of the easier problems we're going to look at. But I want you guys to be thinking outside the box. This is an honors class. This is the kind of problem that you could see on an SAT as like a difficult level problem on an SAT. Okay? Just to keep your mind where you're at. All right, let's go to slide. Inequalities and number lines. So, what's an inequality? It's a comparison. Something is greater than another. Something is greater than or equal to another. Something is less than another, etc., etc. So you know this already. Graph these two numbers and write an expression. Simple. Oops, I am on the wrong one. Let me try this one more time. Graph the two numbers. That's what I mean by you don't have to put every integer, obviously. Here's the first one. Here's the second one. Write an inequality statement. This is a joke. 5 is greater than negative 0.5. How come I know that 5 is bigger than negative 0.5? Because it's to the right. Again, obviously you know that, right? Common sense tells you that 5 is bigger than 4, 5 is bigger than 2, 5 is bigger than 0, because you know numbers. But on a number line, the easy way to think about it is the number to the right is always greater than the number to the left. Okay, these are our basic definitions of inequalities. Absolute value. Absolute value. This means distance from 0 on the number line. That's all it means. The distance from 0 on a number line. So for example, what's the absolute value of negative 12? 12. Because look, here's the number line. How far apart are they? How far apart are those two numbers on the number line? 12 units. You don't say negative 12 units. If I say how far apart, I'm asking you for the length itself, not displacement. In physics, you're talking about negative lengths and displacement. I'm asking for the actual length. That length of the segment that I shaded right here is 12 units. Tristan.
So if the negative is outside, the absolute value of the number is negative 12 still.
Yeah, so if I had, oh my gosh, if I had this, like that, Tristan, you take this, make it positive, but since it's negative, it's still negative 12. Okay? An easy way to remember, general rule, here's your rule. Oops, let me do it this way. Give me one, not even a second, hold on. Okay, that's all I want you to jot down. If A is positive, it's the same number. That's what this means. When A is positive and A is greater than 0, absolute value of A is A. If A is negative, though, what do? You take whatever this was and what do you do to it? Yeah, you make it the opposite, so you make it positive. So again, if A is negative to start, you take the opposite of whatever this is, and that's what you have. If A is 0, anything absolute value of 0 is 0. Okay, these last ones you can obviously do on your own. Tonight, please just do this homework. Okay, again, okay? So this homework is section 1.1 in your textbook. Remember I talked about WE is written exercises. So in your textbook, go to section 1.1, which is right here, and look at your written exercises. That will be page 4. Okay, but I'm not going to give you page numbers ever, so know what I'm talking about. Section 1.1, 3 to 39, multiples of 3.
Isn't it a little?
All your homework is always on Moodle. Always, 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 okay?
Is it tomorrow?
It is due tomorrow. So on Moodle, it will say homework 1.1. How do you know where to find it? At the end of your notes is the actual assignment, always. Okay, on Moodle, it will just say 1.1. You got to go to the homework notes from 1.1 here. Okay?